So we're very good old friends, and I'm so glad that he went into the university, professor at Lund University, engineering faculty.
Yes, engineering faculty at the Center
Let's
for...
see if we have some
We
volume.
soon have,
Yes.
sound now, I think, at the Center for Mathematical Sciences.
Yes.
So the math department, you could say.
Yeah, but then actually the key thing with Karl, well, he knows plenty of mathematics, but he can be very educational. So in gymnasiet, I have to tell this story. When we had our teacher, we all were quite astonished with just after 1 week, he just took all the 3 years mathematics and bang, got it away. He just got an exam in mathematics 3 years, so you got too much time actually, I believe. We all were struggling, and you were having spare time all the time. But I'm not bitter. But then in physics, he was in class. That was a big problem of our teacher, because he knew he had Karl in the classroom. So when the curious, schoolmates, teacher, can you just... They're very tricky questions. And every once in a while, the teacher say, Karl, can you take this one? So it was quite nice to be in school where teacher really accepted that, well, I have a pupil who's much better than I am. So that was a great time.
Oh,
Bertil. So, this is Karl.
Yep.
What's your relationship to digital twins, Karl?
Yeah, that's what I'm going to talk about. I'm going to talk about my research.
Yes.
And my research is a lot about doing models or digital twins of the world.
So, and how much mathematics do we talk about? Is it all mathematics, do you think?
So what I'm going to show here is there's some math, there's some optimization, statistics, programming, physics. There's a lot of things. And also,
but optimization, isn't that math?
That's also math. Yeah.
It's everything's math.
Yeah. Well, yeah, kind of.
So when you talk about Tetra Pak here,
that's math.
Yeah, that's math. It's all about math. And do we need more people, within the companies, very specified in these areas, do you think?
I think you need more people that have studied sort of engineering or natural sciences, but I think you do have those people at Tetra Pak and Alfa Laval.
Yeah.
And I think also if you go to these kind of engineering schools like degrees, you get a very broad competences that you can use at these companies.
Yeah.
But I think also, I'm going to talk about research on making models automatically, computer vision, machine learning things. I think we might use some of those tools connected to what we're talking about today.
Yeah.
But the research is not directly connected to the digital twins or the organization. But I think there are connections, and that's what I'm going to try to elucidate.
And we talk very much about collaborations in many ways.
Yes.
Samverkan in Swedish. And what role does the university have? Because we have all the society and all the companies and all the innovation systems. What role do the university?
I think the university plays a key role in collaboration with society. And I think the strongest factor, the strongest influence is made by the students that we educate. So when they do a master thesis project, or if you have a PhD student that does the research and then goes out in industry, that person or resource then takes all of that knowledge and all of the sort of latest results into the organization. I think that's the strongest thing that we do. But then, we work together with companies and with public sector in master thesis project or in externally funded project or in many ways. Yeah. Like industrial PhD study projects.
And often you think, you're too occupied at the university. Yeah. No, don't bother us. We are researching.
Well, some are like that.
Yeah, but you're not.
No, I like to do samverkan, to do collaborations.
So, and I really feel that at Lund University, your department, you're very interested in getting contact with companies. Yeah. Tell us about your thoughts, what you're struggling with. Can we help out?
Yeah.
So this is me helping Karl get in contact with the world.
Thank you.
More to do. Get him more to do. Okay, great. Leave the stage to you. Yeah. And here's for Karl.
So thank you. Thank you very much. Yes, so I'm doing research on computer vision and image analysis and machine learning. And today I'm going to talk about two themes. So there's going to be lots of images and movies and sort of demos of things. But really, essentially, there are only two things that I'm going to talk about. So I think it's going to be understandable. So after a brief introduction about me, I'm going to talk about the first thing, and that's how do how do humans or animals or machines that we develop, how do they develop digital twins of the world? Because in your head, you have models on how the world works. You can shut your eyes and you can sort of think, if I go outside, there's a room there, and then there's this water there, the toilet is there, and if I do this. So we have some sort of model of how the world works. And we exploit those models to make decisions on what we're going to do. But how do we develop those models? That's an interesting question. And how can we make machines or computer programs that can, just by exploring and doing things, automatically make digital twins of the world? So that's the purpose of the first sort of number of slides there. And we've come quite a lot, I think, in understanding this, and we're working with biologists on understanding animal cognition. We're working with medical researchers to understand humans. But we also do engineering stuff to make machines and programs. But I think we're pretty far away from having some really good real-world applications here. But then in the second half, I'm going to talk about something that is relatively easier. That is how to make models, sort of geometric models of the world. And that's something that I've worked with for a very long time. And there we have, there are applications, lots of applications, and already in industry. But both of them are on how do we make these digital twins, and how can we make them automatically. So the introduction, I'm working at the Center for Mathematical Sciences. It's the building, F building at the engineering school. And we do research at the department on numerical analysis, statistics, differential equations, and lots of different stuff. But we have a pretty large group doing computer vision and image analysis, machine learning. And that's where I and my colleagues work. And I'm doing all of that research. I'm doing teaching, supervising students, and but also I'm 20% of my time, I'm coordinating a network at Lund University that is connecting all AI research at Lund University. And that is also AI research in law. So what are the legal aspects of AI algorithms? It's philosophy, it's medicine, it's economics, and stuff like that. So lots of researchers, different faculties are working together to do fun stuff. But let's move into the first part, natural and artificial based world modeling. How can we do this? How can we, when we're small, we're just a small child, just sort of toddling around, how can we develop these models automatically? That's an interesting, fun question. And there's a topic called machine learning that is such that if you have lots of examples of the input data and lots of examples of the output data, you can automatically learn the function in between. So a natural way to think about how this would work, and it doesn't work, but how you could think is that we have sensors, so we have the eyes and ears and smell and stuff like that, and there's sensors in our body, so lots of input. And we have actions like all the muscles we can stretch and do things with. That's our outputs. So you could imagine that we train, if you get this input, if you see this, then you should do this. But it's very difficult to find what is the best sort of output given a certain input. We don't have that data. And clearly, a child is not given that training data to do it. It has to generate the training data itself somehow. So a better way to think about this is that you have the child or the machine or the car or the program here, that's the agent. What was it? The resource, yeah. And then you have the world. And the child or the person can do actions. It can sort of smell things and chew things and taste things and toddle around. And then it can measure what happens. What happens with the images that I see or the sounds that I hear. Based on sort of random actions and random sensing things, inside us, we have ways of learning and ways of learning models of the world. So this is the digital twin of the world. And obviously, that model is not containing all the details of the world. It has to be a much, much simplified model of the world. But somehow, we are doing this automatically. So by by moving around and discovering that if I stretch my arm like this and I hit the surface, I know something that this can happen if I move like this. That's something we can actually do. And we have a pretty good idea that something like this is happening in humans and animals, but we don't know the details. We're far from knowing what's going on. But in simplified sort of simulations or games, we can try to do this for machines. And I'm going to give some examples here. And there are some other ways to model what's going on inside the agent. There's an idea calling an actor, which is similar to what I said first, that just takes the sensors and the sensing and then calculate what's the correct action giving this input. There's another idea to use a value that says that given this state or this sensors, if I make a certain action, how good is that? So those are other ways to represent this. But I think in this case, the world modeling idea is the one that's most interesting and most similar to sort of the digital twin idea. So we're going to look at some examples here. But when we're doing this learning, it's important that we try both things. We need both to explore things to learn about the world, but also we need to use the digital twin to make the most appropriate action. And in machines and also in humans, there's a constant sort of balancing of these things. So for an example of exploration is if you want to try restaurants, the exploration would be to try a new restaurant, but exploitation would be to go to the restaurant that you know so far is the best. And sometimes you do this, and sometimes you do this. And in other examples here, you can read it yourself. What's also important here is that you need to think about what is the goal. And that's like for companies, that's also important. Is it the carbon footprint, or is it the last line in the revenues, or is it? And you have to sort of figure out what's the goal. And for humans and machine, that's quite difficult to sort of, what is the goal? What is the goal of me? What am I trying to sort of maximize? I don't know. But there are some ideas. In control theory, there's something called dual control, where you assume that someone has given an explicit loss. There's also a theory called reinforcement learning, where it's also assumed that someone has already told you what the reward is. But there are some other ideas, more general ideas, called explainability and empowerment. I'm not going into those, but that can be used almost generally to make these kind of systems work. We're going to look at one example here, and this is a paper by Schmidt-Huber and David Ha. So it's not a real thing. They have a simulated game kind of world where this is the sensor input. So you think it is being like you get some images, like a computer game, and the output, the action is that you can turn the right button or the left button. But the program doesn't know what kind of game this is. It only can do things and discover what happens, what kind of input do I get. So in this paper, they developed a method where you have the environment, which is this simulated, this program, the game. And then it's building up automatically ways to sort of compress the input into something meaningful. It makes memory representations automatically. It makes an environment model automatically, and also it tries to define what kind of actions should I take based on the input. What's interesting here is that once you have the digital model, then you can decouple everything here. You can sort of ignore the reality, and you can do the simulations. And that's what we talked about earlier. You can try things. You can try experimenting with your digital twin and see what will happen. In this case, you can actually run the model you can sort of dream, what would happen if I press the left button? And then in this dream, the learned dream model, you see that it looks something like this. So it doesn't look exactly like the real thing, but it kind of captures some of the important aspects of the real model. So the movie here, the lower movie here, shows you what happens if you run the learned environment model and simulates that. So I think it's pretty interesting and amazing that I mean, it's crude, but it still picks up the important thing that there's usually some car, some lane, and there's usually some grass, and it can turn, and if I use the left and right button, certain things happen. There are some details here. We won't go through all of them, but I will try to talk about some of the aspects here. One of the aspects that's important is that the input here has lots of pixels, there are lots of numbers. So in the eye, you might have several megapixels in your eye. And on the body, you'd have also millions of sensors input. In this case, in the simulated game, there would be like maybe a million pixels. So having all of those million pixels, it's sort of too much. We don't want to learn all of the details in the world. We don't want to remember every grain of sand and every leaf on the tree or something. We have to make simpler, cruder things to make this work. So it's important to do something called dimensionality reduction to actually solve this thing. And that's something they did in this paper. So although you have maybe a million numbers here, you can actually represent the types of input with maybe only 10 or 20 numbers. And using only then 20 numbers, you can still reconstruct the images fairly good enough. So that's an important part of this thing, that you do something called dimensionality reduction. But then there's a nice demo if you want to try these things and see what happens in the dimensionality reduction and see the dreaming and stuff like that. But the final thing I want to talk about is this dreaming thing. When you are simulating, you're using your simulated world, it's important that the action is not coupled to the real world. If you want to experiment, what happens if I tear down the factory? You don't want to actually tear down the factory. You just want to see what happens in my model if I tear down the factory. So it's extremely important that when you sort of use your model to explore different possibilities, you need to decouple the actual action. So that's trivial in organizations, you wouldn't dream about doing that. But it's important in animals as well. So when we dream, when we go to sleep, we play through our internal simulations. So we have internal models, and when we go to sleep, we sort of play around. What would happen if I do this? What would happen if I do this? But it's extremely important when we go to sleep that we decouple the connection to the muscles in the body. What can happen, certain disorders, is that this is not decoupled, so that when you're dreaming, you're actually running around and playing around with your arms. So that's an actual disease, and it's a terrible problem. But the other thing that can happen is that you can have problems with this switch when you are falling asleep. So you're still awake, you're starting to falling asleep, and the switch goes on. So you're now paralyzed. I cannot move my body, but I'm still awake. So it's a super scary condition. And it's called something hypnopomp hallucination. And the same thing can happen when you wake up in the morning. You can wake up, the switch is still sort of, you turn off the switch, you wake up, but you can't move your body. You're paralyzed, and then maybe a minute later you can start moving your body. So it's interesting how the connection between machines and humans here, how it's tightly connected. So that's the first part. How can we learn world models automatically? The second part is digital twins of the natural world in more of a geometrical sense. And this is something that one of my favorite research topics. So this relates also to sensors and world models. So it could, for instance, be that you take a camera and take images, and you have a 3D scene of the world. So given just lots of inputs, maybe images taking of this scene, I want to figure out where is the camera and what's the 3D structure of this scene. But you can do the same thing with microphones. You could have many microphones in a room, and then maybe many sound events. People are talking and walking around. Can you figure out where are all the microphones and where did all the sound events happen in 3D? And you can do the same things for many other different sensor types. So I will now have a few slides where I talk about some of these types and what we've done. And then in the end, I will give a couple of applications where this is used. So first is something I started doing when I was an engineering student. This was my master thesis. We had a laser truck in Luleå with a laser sensor that measured the direction to reflective tapes that we put on the walls in the factories. And then by running around manually, you drove this vehicle manually, then you automatically made a map of where all these reflective tapes were. So that's the world model, the digital twin. And then we use that map to figure out where is the truck at all times. And then we can use control theory to drive the truck autonomously. So this was being used in Tetra Pak factories and many factories, and I think still being used quite a lot. But now there are other more interesting sensors as well. Another interesting sensor is the ultra-wideband radio tag. So you could have tags, and these become like small, you can think of them as being GPS satellites, but you just put them in some factory or some room. And then you also have an ultra-wideband receiver transmitter in the mobile phone or in your mobile unit. So the same thing is here. You first sort of move your phone and make a map of where your sort of mini GPS satellites are. Once you know that map, you can figure out where the phone is at all times. So here's an example of two former PhD students, here Marcus and Kenneth. And here we have two drones flying autonomously. And they are continuously figuring out where they are thanks to these small GPS, ultra-wideband tags that have been placed in the room and that they have sort of automatically measured. We're currently trying to experiment this with the upcoming techniques of having many antennas both at the receiving and transmitting end, so-called massive MIMO antennas. So this is sort of 5G, 6G technique. So together with researchers at the EIT department, we made experiments where we moved around one antenna in this room, and then we had just one transmitting antenna with many small units. And still we tried to figure out how did it move, where is this, but also what's the shape of this room. So something that we ongoing, but sort of lots of interesting stuff there. But you can do it also with a mobile phone and just the Wi-Fis that you have all around in the world. So together with a spin-off company, Combane in Lund, it's a spin-off company from Sony, they have and we are continuously mapping up where are all the Wi-Fis in every building in the whole world. And then if you just measure the signal strength to the Wi-Fis that you have closest to you, you can figure out where you are. And this is experiments made when we walked around the math building and then up in the math building, and it's automatically making this world model of the where the Wi-Fis are. Another example that I like a lot is this sound example. Here we placed 8 microphones in the coffee room at the math department, and I go around and I play a song by Bass Hunter, and then automatically it figures out where are all the microphones and what's the 3D motion of the sound source. Okay, so what can this be used for? One application, sort of not so money intensive, but still, I got a phone call from a German researcher who made researches in bat caves in Bulgaria. And he said, I'm going there every evening, I'm going up in the cave and I'm putting microphones in the whole cave system. But I want to figure out where those microphones are, but also track all the bats as they're flying in the cave. So we made lots of experiments there with the bats, but also putting up all these microphones in the cave and figuring out where were the sound sources and where were the microphones. Lots of fun research, and we're still trying to do more there. But perhaps the most more common use is the sort of image analysis use. That's when you have lots of images. Automatically you find natural landmarks, you match landmarks between images, and then you make 3D models. Where is, in 3D, is every one of these small natural landmarks? And also, where in 3D is where was the camera positioned when I took all of these images? And what can that be used for? We can do it to make 3D maps of the world. So one of my PhD students, Martin Byröd, he worked at Apple, and he are making the programs that make these kind of 3D maps from aerial photographies. Together with Sony, we've made a automatic sort of 3D face scan. So you just took your mobile phone and you could then make a 3D model of your face or of your food or lunch or your pet or whatever. And what can we do with that? Well, obviously you can use the 3D model, and you can take that 3D model of yourself, and you can put yourself in a game. So here's you playing, I can't remember what this one was. My kids know what this is.
He lives in Bjärred.
Yes, he lives in Bjärred. Skyrim, thank you. It's Skyrim. And this is Grand Theft Auto, I don't know, 5 or 6 or something. So if you want to try different clothes or hairdos or sort of those kind of things, you can use this kind of software. Yeah. Or you could take the 3D model. So this is like a 3D model of me, and then you can 3D print it, and you can make painting pieces of it. So here we have Johan. Yeah. And here we have me, and we're playing a new game, Insomnia, where you should stay awake and play games in this house without falling asleep. But obviously, like in the first example with the autonomous vehicle, having autonomous driving is interesting. So we did this with ultra-wideband earlier, but we're also doing this with vision. So we have one of these 19-gram drones that are made here in Malmö, Crazyfly. So again, we made a map using images, and then after you made the map, you can design, this is the route I want to take, and then you can let the drone fly autonomously. For instance, if you want to survey what's on all the shelves so this is in the basement in the math building, so it's not a very fun store, but it's a good experiment place. But we tried it, Axis, they have sort of a mock-up store part of their demo session. So we made these kind of experiments in their stores as well. And we want to make the experiments also at ICA, but we're sort of a little bit scared that the drones would do something bad. But we'll see. But the last example is together with the company Katam here in Malmö. They want to make an automatic survey of sort of digital twin of the forests, you could say, but make it automatically. So there you need to have the autonomous driving of drones if you want to have drones, but you could have just a mobile phone and take images. So there's a lot of sort of technology into that. But then there's also a lot of image analysis to find the trees, measure the trees, how wide they are, identify the trees, what species are there, and so forth, and then GPS tag the trees in the digital twin of the forest, so to speak. So that's the last example. That's where I want to end. These tools, machine learning, computer vision, image analysis, robotics stuff, they're all about mimicking functions of human or animal cognition. And I think many of these have their lots of different applications in industry. But there is this sort of basic understanding question: how do we work? How do the human brain works? That we also want to study more. And we're trying to do more research together with the biologists and the medical and the philosophy researchers to connect the different parts that are interested in the same type of questions. Digital twins, for me, it's really modeling, making models of things and then trying to use those models to make better decisions, predictions, and stuff like that. So this is an exciting area, but we still don't understand natural cognition enough. And with that, I thank you for your attention. Thank you.
Thank you, Karl. Well, fascinating to hear always. I'm thinking about the importance of collecting data, because this is collecting data in different types. Do you have any ideas of of how can we be better at collecting data to being able to
Do the
get
learning
get
here.
get the maths right?
Yeah.
How should we think about that?
I think it's extremely important, but I think most companies are good at collecting some of that data. But it is depending on what application you want to do, what kind of, say, machine learning application, you might need to consider what kind of data do I need to store,
Yeah.
and there are lots of questions there. If it's data that's connected to humans, you have legal and integrity issues that you have to consider. But I guess if you have products, it's easier. So resources, difficult, but products,
Okay,
material easy.
but I believe
Yeah?
I'm thinking of a creative perspective here, and I think it was quite fascinating, the exploration, exploitation
Yes.
perspective. But I mean, when we collect data, we often collect data. Well, that we know that's important.
Yeah.
But it's tricky to know that the data we don't gather,
Exactly.
because if we have bigger brains and knew more, then we would ask different questions. So, do you have any tips? How could you think of collecting the right way? How do we invent the right sensors? How we collect? Well, maybe we're measuring totally wrong things. We should put the
Yeah.
sensor
How do
there.
we find out what things to measure?
Yeah.
Yeah.
So
It's an extremely interesting but also difficult question.
yeah, I
because,
understand that, but it's then the business opportunities are there.
Yeah,
I
but
believe.
that's where I think these kind of ideas, where we try to understand humans, because we are constantly collecting data, we're sort of collecting images and senses and smells and stuff like that, and somehow we're exploiting all of that data and storing parts of it or learning things based on it. So it might be that we could, say, in a organization or in a larger company, also try to see how can we learn things by automatically collecting and exploiting data, sort of.
Yeah,
But it's super important. And I think also what I touched upon, many of the things we do here, they concern sort of one robot or one individual. In an organization, you have the interactions between many individuals. And that's a super interesting research area. How do you get sort of the collective behavior of many individuals to work better together?
Yeah, but because I know, I believe you have some kind of projects when you can use, since Sweden has gathered information many hundred years in following our population, and that is very useful when it comes to research.
It is.
We didn't know that at the moment,
Yeah.
but since we've gathered all the information, we will enable new
We can
solutions.
do more research, do better
Yeah.
research.
So what? Because otherwise, that's not important. No, that's rubbish. Take that away. We don't need that data.
Yeah.
Should we gather more data? Because in the future we might need. We can't really understand it now, but
Yeah.
later on, is that a?
But I think it also depends on what kind of business you're doing. So, for instance, like Sensact and Volvo are making autonomous cars. They are collecting an enormous amount of data from their cars. And I think soon they will have new versions of cars with new sensors, and they will be collecting massive amounts of data.
Yeah.
And they are running and rerunning their programs on those data to sort of verify that they don't break and work.
Yeah, and that's.
But I don't know sort of how what is the correct data to collect at Alfa Laval or Tetra Pak, or I don't know how Ortelius, are you making models of your own company, for instance? How can you prove your own company by making a digital twin of? But maybe those are more difficult questions, so the organizational things.
Can you use the way of collecting data and helping the creative process? We can gather data to be able to come up with the ideas that we will. Otherwise, we will follow the ideas that we have. Can we use that technology, getting new ideas?
I have no. It sounds super interesting.
Yeah,
We
solve
will
it.
solve it together.
Yes. You need coffee, I see. And so do I. Great. Let's see. I'm quite curious. Anyone from Ortelius? Because I would like to, hear. Yes, please. How you can use, in what way? Because you have your world. Take the
Your
mic.
digital twin.
Yeah.
Take the hand mic.
Yeah. So let's go. If you take, what kind of reactions do you? What are you thinking when you listen to Karl? When it comes to what you are, trying to get us to understand from Ortelius?
Okay, so first of all, I mean, these are all really, really interesting aspects and fascinating research areas for sure. But I think one thing to pay attention to is the last point. We don't understand human cognition sufficiently to actually utilize AI, machine learning, those types of consequences to help us. So that and honestly, that's why we exist, because it is software is by definition a model that is incomplete. We cannot model reality. But we get pretty close, and the dynamics of how we model actually is a true reflection of what it is. And then you were into something that I find is really, really interesting, and how you can improve, say, interaction by between people with information and so forth. But I think that we still know too little of what actually is providing effect. What is the cause of improved performance, so to speak? So what we're looking at instead is trying to make knowledge available to the organization so that they can, because we talked about collecting information, right? And most companies do today. The problem is that they collect information. We call it information, and we can call it data as well. But we collect information without context, which means that in a year, when we're looking at what the previous model of Volvo's self-driving car we're looking at, it's not the same that they're looking at now, and we don't know the difference because they were different sensors. They looked at it in a slightly different way. It was a nuance and so on. So it becomes a problem if you don't have context to information. I mean, data centers grow as mushrooms today, and we store more and more. We don't know how to use it, and we will never know how to use it because we need to figure out what context it came from the start. Once we know that, we can utilize the information moving forward.
So from what Karl was talking about, in Origo,
Yeah.
how do you, if you should connect what Karl told us about with Origo, what would
Yeah,
that be?
so I think that what is important to understand is that to really utilize artificial intelligence and the power of computation that we have today, you need to have structure, and that structure needs to be designed. We can go the other way, of course, and figure out if there are patterns, like well, you know, the Panama Papers. Okay, so what are the connections? We don't know that beforehand. We look for connections, but we go the other way around. We say, okay, so what connections are there? And then Origo can produce information that you can apply artificial intelligence on. So, and this was what I meant when I talked about the fact that a data scientist's time is 80% creating order on information. What we're saying is that remove that, leave that to Origo, and let the scientist, the data scientist, actually apply value instead. Yeah. Because sorting out where the stuff comes from is fairly easy to automate. At least if you're Ortelius, it's fairly easy to automate. Right?
I think that, I mean, that's super important. The importance of having ordered data, like you're providing, is sort of the basis for then doing all the fun stuff, sort of the machine learning and the analysis and the modeling stuff there. I think that's good, and that's why digitalization and machine learning goes hand in hand. You need that to make it work.
And let's see if we have a final question in the auditorium. No. Well, there's one. Okay, give me the mic, please.
Absolutely.
Okay. Hello, what's your name?
I'm Philip.
Philip.
Yes.
And your question?
And my question is, in terms of semantics of the models, that is super important. And so in the models that you're creating, how do you think about semantics in the model? Because we want to understand the data that the AI model is producing to know that it's accurate.
Yeah.
So how do you think in those terms to define how much do we need to know about the model to say that it's valid? Yeah. How do you think about these? So it's not that much of an answer, but rather, how do we think about that?
Yeah, exactly. Exactly.
So I think there are many cases where we do things like 3D modeling of the world, or like the geometry part. There we have come quite far, and we can do these models quite good. And we can also put semantics in, because we know what are the important semantic structures of like buildings or road signs or windows and things like that. For the sort of internal first half, with the internal models, if you use some of these other actor critic things I didn't really talk about, they don't contain any semantics at all. They just sort of numbers in, something happens, and then action out, and no one knows what's going on. But when you have these world models, you can at least you can explore, you can run those simulations, and at least see what kind of things are these models good at capturing. You can sort of at least starting exploring it a little bit more. So I don't think there's any good semantics there right now, but at least it is a more better, closer to something we could explore and exploit, I would say.
Thank you so much. Very well done, Karl Åström, Professor. Thank you so much.